Hi there, during this session I'm going to be talking about the ideal gas law. That is, this law here, which we use to describe the actions of an ideal gas. So that's a model gas. We're looking at how pressure multiplied by volume equals the number of moles multiplied by something known as the gas constant times by temperature. Intrinsically in this, we recognize that pressure, volume, and temperature, the macroscopic features, are related to the number of moles, which is obviously the number of particles involved, which is a microscopic feature. So these two things are again linked together using this law. So let me just examine it a little bit more closely. If we think what we can learn from this law. So first of all, the law again tells us that pressure is proportional to temperature. As long as we're thinking about this on a Kelvin scale, so that means that when there is zero pressure, in turn there's going to be zero temperature. And that's something we've seen before with the gas laws, and it's again highlighted with the ideal gas law. So give me an example here. Calculate the volume of 1 mole of an ideal gas at STP. Now that means standard temperature and pressure. So we're going to use standard temperature as 273 degrees Kelvin and pressure to be 1 atmosphere, which is 1.013 times 10 to the 5 pascals. Think about how you do this calculation. So pressure times volume equals the number of moles times R times T. As it happens here, we've got 1 mole of gas, and my constant R is 8.315, and that's multiplied by the temperature, 273, divided by the pressure, and that gives me a volume of 22.4 litres. And you may remember one of the definitions for Avogadro's number was the number of particles found in 22.4 litres of any gas. So these two things are consistent, which is important for us all. If I further think about my ideal gas law, I can break it down. It shows that pressure divided by temperature equals constant, assuming constant volume. Pressure times volume equals constant, assuming constant temperature. And volume divided by temperature is constant, assuming constant pressure. These represent the gas laws. So we have continued consistency with the gas laws, which I've mentioned beforehand when thinking about kinetic theory and how I could link microscopic and macroscopic worlds together. So if we multiply all these things together, we've got to remember that pressure times volume divided by temperature is also equal to a constant if we think about the number of molecules is the same, so no molecules have been added to or subtracted from the total number of molecules. This means that we can also use the idea of PV divided by T equals a constant as a gateway into recognizing in two situations. If the initial conditions and the final conditions have the same amount of gas, no gas has left the situation, I can do calculations using pressure 1 times volume 1 divided by temperature 1 is going to be equal to pressure 2 times volume 2 divided by temperature 2. So here's a question which I guess is to think like that. A mass of gas has a volume of 20 litres at 17 degrees centigrade and a pressure of 1.8 times 10 to the 5 pascals. What will the volume of gas be if the temperature is raised to 357 degrees centigrade and the pressure is lowered to 1.2 times 10 to the 5 pascals? Take a moment, do your calculation, and now here is the answer. As we can see, we're going to start from pressure 1, volume 1, temperature 1 equals pressure 2, volume 2, temperature 2. Please note that we have to make sure that our temperature values are consistently in Kelvin, and it comes out with a final volume of 65.2 litres. We're speaking about this idea about an ideal gas. An ideal gas is not a real gas. Okay, it's very similar to a real gas for most of the time, but it falls down at the extremes. So at high temperatures and low pressures, the ideal gas perfectly or most accurately describes gases, particularly monatomic gases. It doesn't factor in the size of each gas molecule or the effects of intermolecular attraction, and there's what's known as the van der Waals equation, and this does take these into consideration, but we don't need to know about it for IB physics. And obviously it falls down because an ideal gas cannot be liquefied. So we've got to recognise if we reduce the temperature, then gases will turn to a solid, or to a liquid and then a solid eventually, but an ideal gas doesn't fit that situation. So there's an introduction of the ideal gas law, what an ideal gas can be used to describe, or the ideal gas can be used to describe, and finally why the ideal gas is similar to real gases but does fall down at some extremes.